independent attack software, as you have to actually do the reversing and pull your hair out and whatnot. So, like I said, the application agent, it runs as a nondescript service. So there's kind of mild level of concealment, but not that much. And you could take this idea that you have this application agent and a persistence module, and it wouldn't take too much to kind of abstract this into a rootkit, right? If you look at the application agent, runs as a nondescript service, okay, concealment. Phones home and manages helper apps, command and control. Collects inventory data, well, collecting data, surveillance, all right? So you making that switch from one intent to another, it's not that far of a jump. So there are a number of ways you could implement the backup rootkit. So the idea is here you implement fault tolerance so you can survive reboot by instituting a secondary rootkit, a backup rootkit. And there are different ways you could do that. You could just basically install another service, which checks to see that the primary service is up and running. But from a forensic standpoint, that's pretty conspicuous. And if someone does a post-mortem, they're going to see that. They're going to scan their registry, and they're going to see that entry right away. It's going to stick out like a sore thumb. A bootkit like Stoned Again, or God, what's that? The NV Labs also has a bootkit called, I think, vBootkit. And these are a little less conspicuous. But again, if they're doing a post-mortem and they have maybe an initial disk image or they know what they're looking for, they're going to see that the bootkit's there. They're going to recognize it. So again, it's less conspicuous, but it's still vulnerable. So the ultimate is to do a firmware-based module, and I've talked about that. And it's like the vendors like Absolute who do like legitimate inventory tracking software, they don't have a problem with this, but for someone who's, part of an independent lab, or maybe you're, an honest to God professional black hat on your own, it's a lot more work. So again, concessions. We want to survive system restart, and we want to minimize the amount of forensic evidence, but we don't want to have to sit here and go through that painful reversing process to survive in the firmware. So in other words, we want a stealthy, fault-tolerant, but logistically tenable solution, right? So here's one solution. Okay, rather than put your backup rootkit on the same machine, put it on another machine. Stick it somewhere else. Have the primary rootkit emit a heartbeat periodically. The backup rootkit will listen for it. And if it stops hearing the heartbeat, it will assume, okay, either the machine's restarted, or maybe it crashed or whatever, but I bet you the primary rootkit's not there anymore, so it reinstalls. And this leads me to an aside. One thing I've noticed is that the desktop machines of high-ranking executive officers are pretty soft targets, just based on my own experience. These people often have admin rights on their own machine, ostensibly so they can get their jobs done, right? It's like, I have work to do. If I want to install this application, I need to be able to do it. I don't want to sit here and make a help desk ticket or anything for you to come install my stuff, so just give me the rights. And because they're high ranking, even IT directors are kind of at a loss for saying, no, you can't do that. We won't give you admin rights. And it's like, I'm your boss. I write your check. Give me admin rights. So they often end up with administrative rights, and they're not always technically savvy. Some of them are, but a lot of times they aren't. And some of these same executives have a habit of installing all sorts of crapware on their machines. They'll install, whatever they find that looks bright and shiny, and they'll install it. Ooh, a new widget for my desktop. Cool. So these machines are noisy. There's a lot of network activity often. The task list is extensive. And a lot of this is coming down to the fact that for the typical system administrator, it's all about availability. Admins will scream availability, and the assurance and security people will scream security. But for an admin, it's all about ultimately catering to business needs. And this is what makes, I think, the desktop machine is going to be one of the new targets. A lot of times the servers can be carefully guarded. But the data's not just stuck on the server, right? It goes all over the place. It ends up on client machines, If some guy's doing a query or he's typing in his password, which will access the data on the database. And so there was a blog article by Richard Balick called "Protect the Data," where he talks about this. It's not, you can't just isolate the data and just, put your eggs in one basket and watch the basket, because the eggs are going all over the place. You've got to protect all sorts of stuff. And so I think that this desktop as a target is actually, that's where things are headed. And these high-level execs who get admin rights, boy, those desktops are juicy targets. So we wanted concealment, we ended up with shellcode, and we wanted to survive system restart. So we ended up relying on a secondary rootkit. Question? Okay. So let's move on to implementation. How did I actually create the shellcode, the kernel mode shellcode? First thing I had to do was to get the stream of bytes all in one place. I wanted my shellcode. You don't want it to be spanning multiple segments. That will be a nightmare. Just for issues like offset displacements and stuff like that, and address resolution. You want your shellcode to be stuck in one little code segment you can rip out. And then convert into an array or whatever you're going to want to do with it. And I used Visual Studio to do this. There's probably plenty of ways to write shellcode. I promise you, plenty of custom solutions you can use. I decided it would be an interesting challenge if I could take the opposition's tools and subvert them against them. And so I used Visual Studio. I said, hey, how could I write shellcode with Visual Studio? Well, this is how you do it. I use these pragmas to get all of my code into one little section with a custom name, code.code, which is arbitrary. And like I said, shellcode does its own address resolution. So I had basically my own little internal symbol table within this code section. And this symbol table, in terms of the C code, was represented as a C data structure, GD as in global data. Right? And so where did storage actually exist? Well, I had a placeholder routine. And this placeholder routine basically did nothing more than take up space in memory, right? And because I need that space in memory to hold all the addresses that I basically want to import. So at runtime, I cast it, the storage space to the structure. I'm basically imposing the composition of the structure onto this memory. Under the storage space, which is represented by the function, such that if I want to access an address at runtime, basically all I need is the address of the structure, and then an offset which the compiler figures out, and that makes it a lot easier. So all I really need is the address of this global data routine, which is just a placeholder, and the end result is I can take a whole bunch of addresses and really work with them all in terms of just this one address. And so how did I do my own address resolution? And that's like one of the quandaries of shellcode. Is there, how do you face the challenge of finding the addresses of routines that you want to access? Well, I ended up using a technique called the MSR scan down. There's a system registry, a system register, the MSR register, which is guaranteed to have an address which resides in the kernel's the PE image. The kernel itself is really just a Windows PE file, so it adheres to the standard format of the Windows PE file. So this MSR register will have an address that's guaranteed to be in that PE image of the kernel, and which is called scan down because you get that address and then you go down until you find the signature which marks the beginning of the image. And all those files, they have this magic set of values in the beginning, which mark it as a PE file. Once you find those, then you scan back up until you hit the import address table. Then now you've got all the addresses that are in the kernel's image. And you can rip those out, not rip them out, but copy them out as you need to and put them in your own internal symbol table. And in this sense, you avoid having to use the loader. And like I said, the advantage of that is none of the bookkeeping data structures get created or get updated. So another thing I had to work with or deal with is the fact that the Visual Studio compiler tries to be friendly. It tries to help you. It tries to add stuff like buffer overflow checking and type checks and random optimization and stuff like that. And it adds a lot of stuff into your code that you don't want there, you don't need there. And in fact, if you try to write shellcode and there's this stuff in there, it will break it. It won't work. So what I had to do was figure out how to get rid of all this. And so I didn't want the compiler to be helpful. I wanted basically